Okay, so hi there, everyone. Welcome to our videos in abstract algebra. Though I haven't really worked out with this playlist yet, but I will in the future, and maybe in this time. But in this video, I'm gonna talk about the fourth topic in abstract algebra, entitled "Elementary Properties of Groups." Okay, so let's get on to it. Um, Now that we have seen a lot of examples, especially in my class, I have given already examples, different examples of groups. What we want to now see here is to deduce some properties that all the groups share. So the definition itself have some questions or raises some questions. We know that each group has an identity element, but the question remains that could a group have more than one? Right? We know that every element of the group has an inverse, but could it have more than one? Maybe infinity, you know? But, these examples, we know that in the examples, each group have an identity or has an identity, and every group element has an inverse. But remember that examples can only suggest. Actually, there is some saying that, for example, is not a proof. So one cannot prove every group has a unique identity just by looking at examples, but we want the rigorous way to present it. So that is by way of proof. Um, we're then forced to restrict ourselves to the properties that all groups have. That is, we must view groups as abstract identities, or sorry, abstract entities, rather than argue by example, which is not really the rigorous way to do that. So what we want is for the next three theorems, we would want to see or illustrate groups in the abstract approach. So the first theorem that we would like to show in this slides, we want to call it Theorem 4.1. And Theorem 4.1 states that every group has a unique identity or uniqueness of identity. So in a group G, there is only one identity element that is present in every, so meaning in a generally speaking, in all groups, in every group G, there's only one identity element. So we want to show this in way of proof. And let's start with an opening statement that supposing that both E and E prime, I'll call this E prime for now, E prime are identities of G. So stating that uh, in a group, there are two identities, E and E prime. So what we want to do is we want to debunk this by contradiction, that towards the end of this proof, we want to show that E and E prime are actually equal, indicating that there cannot be two identities in a group, indirectly saying that there's only one identity element in every group. So therefore, in this case, let's take a single element from G. Say we're going to take an A in G, and since E is an identity of G, therefore from that we can say that A times E is equal to A for all elements A in G, since E is an identity in G. And also, since E prime is an identity in G, we can also state that E prime times A is equal to A for all A in G, since E prime is an identity. So what we want to argue is we want to show a group of statements or an argument that towards the end, E equals E prime. Okay. Now, what we want to do is, let us say we take for statement one here, let me clear out my writings. For statement one, take E, or A rather, and let us say that A is equal to E prime in statement one. If that's the case, we can therefore see, let me write it here above. Statement one will show, if we're going to take A equals E prime, this will become A, E equals A. Then it will become that A, sorry, not A. Since A equals E prime E equals E prime, right? So we're going to bank on that for now. And for statement two, let us take our A this time, and let's take A in statement two to be equal to E, okay? And that's okay because both of them are identities in G. So from statement two, what we have is E prime A equals A, then it will become E prime E equals E. Now take a look at those two statements. Taking this, it yields us, take a look at this one here. From statement one above, E prime E is equal to E prime. And for the statement two below that, E prime E is equal to E. So since we know that E prime E is equal to E prime E, this shows that from the first statement, E prime is therefore equal to E, thus stating that E prime equals E. And that's the argument for this proof for theorem 4.1, showing that E prime and E are equal by that argument. Hence, there cannot exist two identities in a certain group, but there should only be one identity that is E. Okay, so I hope you got that argument right there. Okay, so some remark from this, you may take a screenshot if you want some notes on the step-by-step, because if I'm gonna delete the writings, uh it will turn out to be like straightforward or trivial for some, but I want to show that it's really their E prime is equal to E. So I'm gonna delete this now. Notice that if I'm gonna delete it, that will be the proof. It's not really that clear for some, so I want to illustrate it using a pen. So I will show a remark right after this. Because of this theorem, we may unambiguously speak of the identity of a group and denote it by E. We used E because it is the German word for Einheit. Okay, so German word for identity rather, which is Einheit. So hence the letter E. From here, let's now discuss theorem 4.2. And theorem 4.2 is about cancellation. We cannot simply cancel elements or arguments in groups. But let's read this. In a group G, the right and left cancellation laws hold. So that is B times A equals C times A, which implies that B equals C. And similarly, AB equals AC implies that B equals C. So notice, let me just explain this very quickly in the most practical way. When we cancel in groups, it should be that both elements or both entities should be both on the right side of the equation, so that we can state that the unique left sides are equal. Similarly, on this part here, both are on the left side, so that we can cancel, and what is left is on the right side. Okay, we cannot, meaning in this theorem, we cannot do something like AB equals CA and then deduce that B equals C like in algebra. So this does not work in groups. It should be both cancel. The element that we want to cancel will be both on the right side and both on the left side. Okay, now let me please clear this out. And of course, we want a proof to show that this is always true in all cases. So let's start with our opening statement. Suppose B times A is equal to C times A. So therefore, and we will let A prime to be the inverse of A. So what we want to do is we want to multiply A prime to both sides. It will yield us, if I may, I will just write down on the top part here. So BA equals CA. This will yield us by multiplying A prime to both sides, to both right side of the equation. So we have BA A prime equals CA times A prime. Since groups have the property of associativity, therefore we have B times A prime equals C times A prime. And since we know that A times its inverse, we will have B equals C for that matter. And for the next part, the multiplying on the right side of A prime will give us A prime equals C A prime. So we have skipped a bit of things here. So this yields B equals C as desired. We can also show this. We can also similarly prove the other way, the other one. I mean, we have proven this statement only. We want to show this one. So let's try that. I'll call this statement one. This will be statement two. Statement two shows AB equals AC. Multiplying A prime to the left side this time, what we have is A prime times AB equals A prime times AC. And this will yield us, by associativity, we have A prime A times B equals A prime A times C. A prime times A, its inverse is equal to E, the identity. So therefore, B equals C as desired. So by case, if you want to be very strict with that, by case one and case two, the theorem is proven. Therefore, right and left cancellation laws hold. Okay, so I hope you can see the writings above. I would suggest as well, if you want to take a screenshot, by all means, please do so. Okay, now I'm gonna delete this. Okay, I hope you have the screenshot already so that it will be clearer on your side. Now, a remark for this cancellation laws. A consequence of this cancellation property is that the fact that in the Cayley table, or in the table of operation in abstract algebra, for each group element occurs exactly once in each row and each column. So that's why it behaves like a Sudoku type because of this property. There's only one element for each row. That element A, for example, is only once, can only be seen once in each row and in each column of the Cayley table. Another consequence of this cancellation property is that every element in a group have a unique inverse. So let's talk about that in theorem 4.3. So this talks about that every element has a unique inverse, or uniqueness of inverses. So the statement says that for each element A in group G, there is a unique element B, which is also in G. Of course, closure should be seen, such that A times B is equal to B times A, which is equal to your identity element E. So let's prove this. Let's start with an opening that we're supposing that both B and C are inverses of A. Again, this is a proof technique called uniqueness proof. And the gist of the proof is like, let us say that there is no unique element, meaning there are two elements. And towards the end of the day, we want to show in the proof that these two unique elements are equal, indirectly saying that there's only one unique element in every in this property. So this property, we have two inverses, B and C, and what we want to show towards the end is that they're equal. So if both of them are inverses of A, therefore it will be clear that A times B is equal to E, and A times C is equal to E, because B is an inverse of A, so therefore it's equal to E. C is an inverse of A as well, so it's equal to E. So this shows us that AB equals AC. Now, I guess you know what will happen next. By using theorem 4.2, or the cancellation law, or cancellation property, we will want to multiply A prime in both sides of this equation. So I'm gonna write this again here. So multiplying A prime in both sides. So let me write first AB equals AC, then A prime times AB equals A prime times AC. By associative property, therefore, what we have is A prime A times B equals A prime A times C. A prime times A is equal to the identity. As desired, we have B equals C. So therefore, it shows that they're equal. Hence, there should only be one unique element, B, because B is anyways equal to C. Right? So therefore, if you want to copy the notes about,
alert from your desk is almost full.
Please copy. So I'll delete this now, and let's move on to the next part. Our remark for this theorem 4.3, or uniqueness of inverses, is that as was the case in the identity element, it is reasonable in view of the uniqueness of inverses to speak of the inverse of an element G of a group. So we may in fact, unambiguously denote this symbol here, g raised to -1, as g inverse. Okay, that's a common term in abstract algebra. This notation is suggested by that used for ordinary real numbers under multiplication. Similarly, when we have a natural number n, the associative law allows us to use g raised to n to denote that this is equal to g times g times g n times. So just a little bit of a differentiation in terminologies and notation in abstract algebra. So in the multiplicative and additive groups, we need to, let me delete this. We define g raised to 0 as equal to the identity, because g raised to 0 is 1 in the real numbers, and 1 is the identity element in groups. So when n is negative, we simply define g raised to n as g raised to g inverse raised to the absolute value of n. And for example, g raised to -3 is actually g inverse raised to 3. And unlike in the real numbers, in the abstract groups, we do not permit actually non-integral exponents like g raised to half. So we don't do that in abstract groups. And with this notation, the familiar laws of exponents will hold. So if I'm not mistaken, this is the law of product and the power of a power. Okay, so for all m and n in the integers and any element g in a group, we have g raised to m times g raised to n is equal to g raised to m plus n, adding the exponents. And similarly, power of a power, g raised to m raised to n is equal to g raised to m times n. And although the way one manipulates the group in expressions g raised to m, g raised to n, and g raised to m times, g raised to m raised to n coincides with the laws of exponents for real numbers, it does not hold in involving two elements in group G. Okay. Then, thus the groups in general, generally speaking, AB raised to n is not equal to A raised to n, B raised to n. But there's a nice property which I will show before the end of this video, the shoes socks property, so that to show what works. So let me delete this now. Next is also just a note of caution. We must be careful with this notation when dealing with a specific group, especially if addition is denoted by plus. In this case, the definitions and group properties expressed in multiplication must be translated into the additive notation. So for example, the inverse of g is now written as this, not as g raised to -1, because that's for the multiplication side. G raised to 3 means g plus 3, g plus g plus g plus g, meaning g is done added 3 times, and 3, this is usually denoted by 3g, and g raised to -3 means -g plus -g plus -g, and can be written as this. So when the additive notation is used, do not interpret n times g as combining n and g under the group operation. Note that n may not be even an element in the group. So this is just, adding g n times. So don't get confused with that. So the table next slide shows us the summary of everything. So as in the case for real numbers, a minus b is abbreviated as a plus -b. So this is sorry, let me delete that. These are all the properties for multiplicative groups and additive groups so far. Their identity and their additive inverse, their multiplicative inverse, their power, and their difference as well. So you may have this in your notes so that you'll have the copy. And as a final remark, because of the associative property, we may unambiguously write the expression A times B times C as follows. So remember, the associative property or associativity means that changing the grouping doesn't necessarily change the result. So A times B times C can be written as A times B times C, meaning multiplying or operating A and B first and C, or A times B times C, operating B and C first and then A. In short, we can have a general associative property which holds in these types. So for example, we have a squared b times c times d b squared. It can be rewritten as this or this or this. But though take note, groups are not necessarily commutative. So we cannot necessarily combine this b squared here, b squared element into the b, which is within this operation. So that's not always necessarily true. So always remember, associativity is only for the order and not necessarily for the associativity, let me say that again. Associativity is only for the grouping, not for the order. So not all groups are commutative or not. Yeah. If it is commutative, we call that abelian. So although groups do not have this property as noted here, so a times b raised to n is not equal to a raised to n, b raised to n, though there's a simple relationship that follows. So a b inverse is equal to a inverse and b inverse, not equal, but a b inverse is equal and a inverse and b inverse. So we'll end this video with theorem 4.4, or the Socks-Shoes property. And this shows us that for any elements a and b in G, or in any group elements a and b, AB inverse is equal to B inverse A inverse. Okay, so how do we show this? First, we would like to show, we will want to prove this. Okay, so for this, we know that since we have AB, right? So consider AB to be in G, since A is in G, B is in G, so therefore AB is closed to be also in G. We know that if we have this element, AB inverse should be equal to E, right? Because we're just multiplying it to its inverse. So it should be equal to the identity element. And clearly, if AB times AB inverse is equal to E, we should be able to show that AB, we want to show that, they're equal, right? So this AB inverse should be equal to B inverse A inverse. So it should look like B inverse A inverse should also be equal to E. That's what we want to show. So using the theorems, the using associative property and regrouping, what we have is, then we have A, B, B inverse. So what I did is I regroup the B and B inverse into one. A inverse. B, B inverse is equal to E. So we can just cancel the E, so that by the cancellation property. So what we have is A. If you want, I can just write the E so that it will be little by little. This is equal to A inverse, and A inverse is equal to E. So therefore, notice that this AB inverse shows us E if operated with AB, but at the same time, the group or the element B inverse A inverse also shows and ends up with E as given below. So this therefore lets us know, or tells us that since, well, clearly E is equal to E, then AB inverse is equal to B inverse A inverse, because when we operate this with a lone element with the same element AB, it both gives us E, or it both ends up with the identity. So therefore, I guess that ends the theorem, and that proves our point that they're equal. Okay. So that's it. If you want another proof, and you want it to be even more complete, there's another source that states that we have this kind of proof. I would let you um, read this, and it shows a similar power as before. And yeah, I think that's it for this video. And I'm gonna end it a while. Hopefully you got the bits that I've been saying. By the way, before we end, I would like to explain the socks shoes property. Why it is called socks shoes property, because it's an analogy to how you wear your socks and your shoes. So when you wear your socks, you put on your socks first and then your shoes, right? But when you take them off, you take off the shoes first and then the socks. So just a bit of analogy for this. Take um take A as the shoes. Sorry, the socks, and take B as the shoes. So when you put on your socks first and then your shoes, the moment that you take them off, you take the shoes first, followed by the socks. Okay, and that's the socks shoes properties for everybody. Okay, I hope you got the idea. And that's it for this video. I hope you learned something. Thank you very much for sticking with me through the whole process. And that will be the 4 elementary. I'm not saying that those are all the properties of groups. There are also different and unique types of groups, like permutation groups and cyclic groups, the hydral groups, and they have their own properties that are interesting. And for generic all types of groups, these are the elementary properties. But I'm not saying that these are the only properties. So thank you very much. I hope you learned something, and see you in the next video. Bye.